Hi, this is Dr. M. Brahmayya, Associate Professor of Chemistry, Department of SNH, MLR Institute of Technology. I am going to talk about water and its treatment. And today's overview is some problems based on hardness in different units, how to remove permanent hardness of water with different techniques. So, here the problem is 1. A sample of water is found to contains following dissolving salts in milligrams per liter: magnesium bicarbonate, calcium chloride, calcium bicarbonate, and magnesium sulfate. These are the impurities or hardness causing salts in the given problem statement. So, while we are calculating about this hardness causing salts and how much hardness is caused in the water given sample, we have to calculate temporary hardness and permanent hardness. So, we are going to talk about its answer now. So, name of the given hardness causing salt is calcium bicarbonate, magnesium bicarbonate, calcium chloride, magnesium sulfate. The amount of hardness causing salt in the given data: calcium bicarbonate is 81 here, magnesium bicarbonate is 73 here, calcium chloride is 111 is here, magnesium chloride is 95 is here. These are the salts they have given to us. So, what are the molecular weights of the given salts? For example, molecular weight of CaCl2. CaCl2, Ca, calcium, atomic number 20, and calcium is 17. So, while we are calculating its atomic mass unit, accounts for any atom, its mass, atomic mass will come from protons, neutrons, and slight contributions of the electrons and nuclear binding energy. These all are the mass factors of the particular atom. So, like that, CaCl2 comes for 40 plus for calcium is 40 atomic mass, Cl2 2 into 35.5. Each chlorine carries 35.5 atomic mass. So, it is now overall CaCl2 is 111. It is 111 atomic molecular weight. So, now amount equivalent to CaCO3 equivalents mg per liter. So, when we are going to calculate about in the equivalents of the calcium carbonate, we have to multiply with amount of hardness causing salt. How much data he has given? 81 into calcium carbonate weight, equivalent weights calcium carbonates 100 by the molecular weight of the hardness causing salt 162 for calcium bicarbonate. Sorry, it is a 2. It is not mentioned here. It is also a 2. Likewise, 73, the given value for the magnesium carbonate bicarbonate 73 into calcium carbonate weight, molecular weight 100 by 146, molecular weight of the magnesium bicarbonate. Likewise, 50 for this and 50 for this, and for CaCl2 it is causing 100, for MgCl2 it is causing 100, MgSO4 it is causing 33.3 in the equivalence of the calcium carbonate. Now, temporary hardness. The temporary hardness causing salts, what are the temporary causing salts? Bicarbonates of magnesium and calcium. Now, 2 bicarbonates they have given. The value In calcium carbonate equivalents, we found already it is a calcium bicarbonate is 50, magnesium bicarbonate is 50. So 50 plus 50 gives rise to 100 ppm. This is the temporary hardness of the particular given water sample with the given data. Next, permanent hardness. Permanent hardness is caused by magnesium sulfate, magnesium chlorides, calcium chlorides. These are the salts, permanent hardness causing salts. So we have permanent causing salts CaCl2, MgCl2 and MgSO4. Now 100 is for CaCl2, 100 is for MgSO4, MgCl2 is 33.33. So 233.33 ppm of hardness is caused by these salts. This is the permanent hardness of the particular given water sample. So now total hardness, temporary hardness plus permanent hardness. Total hardness, how much we got here? 100. And permanent hardness, how much we got? 233.33. So overall it is 333.33 ppms. This is the problem how to solve with the given data. Next. So problem 2. A sample of water is found to contain following analytical data in milligrams per liter. Magnesium bicarbonate 14.6, magnesium chloride 9.5, magnesium sulfate 6.0 and calcium bicarbonate 16.2. These are the weights, gram molecular weights of that particular hardness causing salts in the given data. Calculate temporary and permanent hardness of the water in parts per million, degree Clark's and degree French. In different international units, you have to calculate that problem. Now, name of the hardness causing salt, amount of hardness causing salt, molecular weight of the hardness causing salt, amount equivalents to the CaCO3 mg per liter. This is the tabular alignment. One is calcium bicarbonate, second one is magnesium bicarbonate. We have to write down accordingly the temporary hardness causing salts and permanent hardness causing salts. If they are asking temporary or permanent hardness is also, they will be mentioned, they may not be mentioned, but we have to choose like first one is temporary hardness causing salts and second one is permanent hardness causing salts. So likewise we have to write down the salts. Then we have to write down the amount of hardness causing salts, what they have given the data. 16.2 for calcium bicarbonate, 14.6 for magnesium bicarbonate, magnesium chloride is 9.5, magnesium sulfate is 6.0. Likewise, the molecular weights of the calcium bicarbonate. As we calculated like CaCl2, we have to calculate the CaHCO3 twice molecular weight, calcium bicarbonate molecular weight, and 146 for magnesium bicarbonate, 95 molecular weight, magnesium chloride, magnesium sulfate 120. So likewise, when we are calculating the given samples hardness causing number, gram molecular weights, 16.2 into 100 is calcium carbonate, 162 is molecular weight of that particular given salt. This is 10, this is 10, 14.6 into 100 by 146, 10, 9.5 into 100 by 95, it is also a 10, 6.0 into 10 by 120, 120 is molecular weight of the given salt, so it is 5. If you observe here, it is all are 16.2 the given value and the molecular weight is 162, and the 14.6 the given value, molecular weight is 146. So it's very simple calculations by dividing with its same molecular weight, almost it is in hundreds, it is in 14.6. When it is multiplied by 100 calcium carbonate, then it will become very easy to calculate. So that calcium carbonate is a standard reference for the hardness causing salts to calculate the total hardness either by permanent or temporary hardness. In terms of total hardness, we can calculate like this. So temporary hardness is now bicarbonates, magnesium bicarbonate, calcium bicarbonate, 10 plus 10 equals to 20 mg per liter or 20 ppm. So when we are converting this 20 ppm into degree Clarks and French degrees. So 20 into 0.07 degree Clarks equals to 1.4. 20 into 0.07 degree Clarks equals to 1.4 Clarks. Permanent hardness, MgSO4 and MgCl2 are the permanent causing hardness salts. So how much we got? It is 5. Here it is 10. MgCl2 is here. So overall 15 mg per liter or 15 ppm. Now when we are converting into the degree Clarks and French degrees, we will follow the same. 15 into 0.07 degree Clarks equals to 1.05 degree Clarks. 15 into 0.1 degree French degrees equals to 1.5 French degree. This is the how we can calculate the hardness of the given sample and how we can convert the units into different international units. Next, how to remove the permanent hardness of the water. Here, permanent hardness of the water caused by calcium, magnesium chlorides, sulfates can be removed using the methods such as the washing soda process, the ion exchange method, and the use of the chelating agents like Kalgan and synthetic resin methods. These methods work by converting the soluble calcium and magnesium salts into insoluble precipitates or by exchanging the hardness causing ions with less objectionable ones, effectively softening of the water. Generally, we are using water geysers and washing machines in the home. When we are using, if the hard water is present in that particular home, that will be causing the spoiling of washing machine or geysers. Then how to remove this hardness causing salts? By using different chemical techniques or analytical techniques. So when we are going to talk about removing the hardness, there is a first method is treating the water with washing soda. Next method is Kalgan's method. Third method is ion exchange method. Fourth method is synthetic resins method. These are the four methods generally we will use for the removal of hardness causing salts or softening of the water. If you see here, this is hard water. After softening with the different chemical methods or different methods, you will get the water is very pure. Likewise, we have to soften the water from greater than 200 ppm of the hardness to reduce it to 0 to 150 ppm, below 150 as per the WHO rules and regulations. The hardness of the water should not be greater than 200 ppm. So currently, after treating with these chemicals or these different methods, the water will become softened. We will discuss now how the methods will be taken into account to soften the water. First one, carbonate conditioning. In low pressure boilers, scale formation can be avoided by adding sodium carbonate to boiler water. For example, calcium sulfate is a permanent hardness causing salt. When you are adding sodium carbonate, it will become CaCO3 plus Na2SO4. It is a calcium carbonate removed as a calcium removed from the calcium sulfate to calcium carbonate, and Na become Na2SO4. It is a dissolvable salt in water. So likewise, if suppose CaCl2 plus Na2CO3, if you treat the hardness causing salt having CaCl2 in water, hard water, you have to remove this salt by adding this Na2CO3, carbonate conditioning. So this is the method how it will become like CaCO3 plus 2NaCl, like it is a dissolvable salt in the water. Likewise, we have to remove the hardness causing salts by using carbonate conditioning method. Next, Kalgan's method. This is one more method to soften the water. The Kalgan method is a water softening process that removes the permanent hardness of the water by using the sodium hexametaphosphate Na2, Na4, PO3, O6. The active ingredient in the product Kalgan to chemically bind with calcium and magnesium ions. When sodium hexametaphosphate is added to hard water, it forms a soluble complex with these ions, which prevents them from precipitating as a scale or sludge, thereby softening the water and removing its permanent hardness. So what is this use of this chemical? Actually, the chemical structure is like this. Sorry. This Na plus and O minus. This is the structure of sodium hexametaphosphate. This usually becomes, when you are adding this sodium hexametaphosphate to the hard water, initially it will give 2 Na plus ions and Na4, PO3, 6 2 minus ions. Now this will become this will become this sodium ions makes the water free from hardness. How? We have to check. Initially it loses its 2 Na plus ions, and then this Na4, PO3, 6 2 minus ions are there. This ion will react with M2 plus ions. What are these M2 plus ions? Ca2 plus or Mg2 plus. So these Ca2 plus or Mg2 plus ions will react with this anion by releasing one more time, releasing 2 Na plus ions, and it will become like complex. This is the metal ion where Ca2 plus or Mg2 plus. Likewise, in each time it loses its two Na plus ions and it makes the water free from this particular hardness causing salts by making a complex like anion. This is how the Kalgan method is utilized to soften the water. Next, ion exchange method. In this method, we add a pyrimetite, a complex inorganic salt called zeolite, same like Kalgan method. Sodium aluminum silicate, aluminum Na12, silicon pentoxide to the water, which is insoluble in water. On adding this to water, the ion exchange process starts between it and the calcium and magnesium ions. They will be interchanged or exchanged. They will be removed by taking the sodium ions. In this way, the water becomes free from the hardness causing salts. This is also like only Kalgan method. Both are almost same. A specific application of the ion exchange method that uses synthetic ion exchange reagents as the solid material. For example, if you check this ion exchange process, you can look at here a specific application of the ion exchange method that uses synthetic ion exchange reagents as the solid material. These cation exchange reagents. These are mainly polystyrene polymers which contain acidic functional groups like COH or SO3H, sulfonic groups. The acidic functional group is capable of exchanging its H plus ions with cations present in the water. For example, if you look at here, this is an acidic resin. This is an acidic resin. This is a hardness causing salt. So here is a hard water. When we added this acidic resin to the hard water, then we can see here this is a acidic sulfonic group. This is a sulfonic group. This is a acidic resin. The Ca2 plus ions will be catched by these sulfonic groups by removing these hydrogens, and it can form SO3 minus Ca2 plus like this complex, and this will be exchanged, ion exchange reagents. These 2H plus ions will become like this. Likewise, Mg2 plus R2 Mg. What is R2 here? It's a acidic resin. From this acidic resin, alkyl group or something polymer, it will come like R2 and Mg complex. 2H plus ions will become. So it is catchy towards to remove the calcium or magnesium ions by using the acidic resins. These acidic resins are very important resins to remove the or to soften the hard water to the soft water. Next, anion exchange resins. In this method, we can check these are mainly polystyrene polymers which contain basic functional groups like CH2 tetramethyl hydroxide, ammonium hydroxide. Sorry. This is a trimethyl. This is a trimethyl ammonium hydroxide. CH3. Groups like trimethyl hydroxide. The polystyrene polymers which contain basic functional groups. This is a base. Ammonia is a base. So, like a buffer. So, this will be added to the hard water. It will remove OH minus ions to interact with chloride ions. This is a basic reason here. Basic reason. It is interacting with hardness causing salts. When it is interacting with hardness causing salts, the ions will be exchanged. The anions will be exchanged. This is also OH minus is a anion. Cl minus is also a anion. When we are interacting with both of them, hard water and resin, then the Cl minus will come to this place. OH minus will be removed. Here, see, sulfate ions are removed by this resin, polymer resin. Anion exchange is happening here. OH minus ions are releasing. This SO4 2 minus and this Cl minus ions are coming towards to this ammonia part, this basic ammonia part. Likewise, we can soften the water. So in the summary, the lecture covers the topics on the calculations of the hardness of the water in different international standard units like French degree, Clark degree, and milligram per liter, mg per liter, parts per millions. This lecture is also covered the topic how to remove the permanent hardness of the water. These are the topics we covered today. Thank you.